What is up, you guys? So in this one, we're going to build up on the previous lecture, and in particular, we're going to be talking about data races or race conditions and mutex. So a really popular example that is given throughout textbooks is the following. Say I've got a function called myfunc that simply prints 0 to -10 downwards. So cout, call from t1, which is a thread that we'll define later on in the main, and just print my I and go to a new line. In the main function, I'll call thread t1, pass it myfunc, right? And in the main thread, I'll also, but this time print from 0 up till 10, call from main. Okay? Last but not least, I'll join my thread. Okay? So running this, first let's clang, and next let's run. So as you can see right here, main, 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 and so on. There's T1 joining or call from T1 right here, because as you can see, main is still printing, and then T1 joins right here, prints right here, and the 0 from T1 is over here. Let's run it again, and things start to mix. Again, it doesn't give the same output, of course, because it's messed up, right? Here's again and again. Look at this one. And here, okay? Now the reason this is happening is that we have two threads running. The T1 thread, myfunc, which is attached to myfunc, right? And the main thread, right? And both threads are racing, we say racing, for common resource, cout. So this is what race condition is. So race condition is that the output of a program depends on the execution order of one or multiple threads. And typically, race conditions are not good for our program. Usually programmers do not like race conditions. We like to avoid it. So one solution for race conditions is using mutex to synchronize access to common resource. In this case, cout. First, to use mutex, we have to include it, like iostream, so as thread. So include mutex. Then create a mutex. The way you can do this is just over here, standard mutex mu. Then create a function called shared print that takes a string of message and then takes an integer ID, let's say. And both T1 through myfunc and the main thread are calling the shared print instead of using cout. So shared print as such. So let me pass this as a string and I as an ID, as an int, right? Same thing over here. Okay? It's sort of, you're defining your own cout, a shared cout or shared print to organize usage of the cout between threads. So shared print, it should print the message, right? As such. But before it prints the message, just before, it should lock the mutex so that when it's, printing the current message, other threads shouldn't interfere while it's printing, while it's using the cout. So it's kind of locking on the cout. And after it prints and it's done, don't forget to unlock so that, other threads could access and print. We don't want to lock on everyone else, right? Once we're done, we unlock. Once we're using the resource, the cout, lock, I don't want anyone in. I want to block myself, isolate myself, so that no one disturbs me, okay? When I'm done, I open the door so that other threads could come in. Formally speaking, we're synchronizing the usage of cout between two or multiple threads. So we're preventing two or multiple threads to use the cout at the same time, simultaneously. So let's run. First compile using clang. There you go. Now run. And there you have it. You see that main prints, and then T1 prints, and then main prints, and then T1 prints again. So they're sharing. It's shared. It's not that main finishes and then T1 starts or vice versa. No. because when main is executing, T1 is free waiting for its turn. Okay? Now when T1 is using the cout, main is in turn waiting for T1 to finish so that it executes again and again and again. Okay? There is no messy output. It's all so clear what's going on, right? This is how Mutex is used, and this is what it solves, okay? It synchronizes the access of common resource. However, even though it's too beautiful, there's a problem over here. What is it? What if this line of code throws an exception? Then our Mutex mu will end up being locked forever. It will never reach this line of code. Line 12, never going to be reached, hence mu will never unlock. It's as if, you lock the door and the key, you ate it and you swallow it, just like in cartoons. So if there's a certain error or exception, you'll be locked forever. We don't want that. We'd want to avoid that. So leaving code as such is super bad. So it is highly recommended not to use this nor this directly. Instead, we'll use a standard lock guard and a standard mutex. Guard mu. And here again, as in the previous lecture, we're using RAII. Resource acquisition is initialization technique. Whenever the guard goes out of scope, the mutex mu will always be unlocked with or without exception. There's another problem with this though. The resource cout is not completely under the protection mutex mu, because cout is a global variable seen by everyone, and other threads could still use this resource directly without going through the lock. In order to completely protect the resource, a mutex must be bundled together with the resource it's protecting. So a more realistic case is the following. So let's remove this, keep my function right here. Let's define a class as such. Let's say the class called log file, and got a mutex over here, call it m, and an off stream, call it f. Let's define a constructor right here, f.open as such, log.txt, and a shared print is defined here as follows. So string, it's passed this time ID and int value. Okay, so right here we're going to lock onto the mutex, right? Then with the off stream, I'm going to print from ID, so it's either from the main or from the thread, with the passed value. So locker on the mutex m, and then print from the ID, which is either the main or the thread, and its corresponding value. Now it's yelling at me over here. I don't think I know why, or I do think. Let me just include string for a moment. Now let me include, it's still yelling at me. Well, I think the thing we have to include is f stream, and there you go, solved. So let's go ahead in the main function and define a log file log. Okay, I'll pass it here by reference. Okay, hence my func will take a log file by reference log, and we're calling the log function shared print, or method shared print. Not only this, the main function will also call log.sharedPrint as such. So it's yelling at me over here. Well, so we don't have a semicolon right here, solved. Now, nobody could access f without going through this log mechanism. However, you need to maintain this level of protection when you call the class of log file. There are things you should never do. For example, never return f to the outside scope. For example, you should never have a function like this, ofstream reference get stream, and inside this is a getter for f, so return f. This is very bad because the user will get the opportunity to access f without going through the mutex. So this is 1, and 2 should never pass f as argument to any provided function. For example, let's say there's a function void process my f stream, which takes a function void fun of stream and then call a function on f. Because once you do that, function fun could do a lot of bad stuff to the resource f. It can print things to f without going through lock. It could copy f, for example, to a global variable so that everyone else could access f freely. It could also close f so that no one else could write to f anymore. So the resource f is really out of control. Now let's say I have used Mutex to synchronize the access of my resource, and I have also followed all the guidelines of not leaking the guideline to the outside world. Will that guarantee that my program is safe? Now let's consider another thing. Let's consider a class stack. Now as we know, the class stack provides, among other APIs, a pop function, void pop, pops up the item on top of the stack, right? And let's use the data type int that returns the top item. And there's some other functionality as well. And let's say that stack uses an array integer to store the data and a standard mutex to protect the data. And let's assume both pop and top will access the data through mutex, and the stack doesn't do anything to leak the data to the outside world. Then in my func, it would take a stack as such, call it s, and in this function it would do int v equal to st.top and then st.pop to pop off the item, and then call some function to process v, let's say. Now my func will be used to launch a bunch of threads, and other threads will share the same data s. Now, the big question is this code thread safe? Now, let's consider the case. So let's say this is my stack, and I've got thread 1, 1, and thread 2. So my stack at the moment looks like this. So I've got a 9 over here. This is my data, 3, 8, and a 6. Let's say in the thread, I've got an int v, which is s.top, calls the top of the stack. Then I pop my stack, so s.pop, I remove 6. So the output here is 6, right? I pop it, and then I process, a v. Whereas in thread b, right just here, I've got an int v, that is s.pop, and just between those two lines, I've got 2 lines of code right here saying s.pop and, process v as such. Let's say thread 1 executes first. It accesses the stack right here. It returns 6 and puts it in v. Then thread 2 will call s.top and put it in v. It will return 6 as well. So this is step 1, then step 2, then the compiler is here. Then we pop s, the stack s. So 6 is out. Then we're here. 8 is popped out of the stack. After that, thread 2 will call process v, and then thread 1 will call process function. As you can see, the number 6 was processed twice, and the number 8 was never processed. 8 was lost. So apparently our code is not thread safe. So how did this happen? We have used Mutex to synchronize the access of the data, and we have not leaked our data to the user. Why is my code flawed? It's not safe. In this case, the one to blame is actually the interface itself. The interface is designed in such a way that it is inherently not thread safe. Now, the operation of top and pop should not be separated into 2 operations. They should be combined into one function. So the simple solution right here is let the pop function return integer data, and function 1 will call pop instead of top. So let's return an int over here. It pops. We remove this. Now this code is thread safe, but it should be pointed out that this function is not exception safe, and that is why the STL stack containers pop function doesn't return a value, But that is not our interest right now. We'll talk about this in future lectures. So that's it for this lecture. So what we did was talk about one particular race condition that is called data racing and techniques to avoid it, such as a couple of things you can do, which is let's one, using Mutex to synchronize data access and never ever leak a hand of the data to the outside scope. Okay? And last but not least, how to design your interface properly, as we saw in the stack example. That's it for this lecture. I hope you enjoyed it. If you found this lecture beneficial, please subscribe to the channel and leave a like on the video. If you have any questions whatsoever, kindly leave a comment and I'll make sure I'll get to it as soon as possible. Thank you so much, and I'll see you in future lectures.